Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay. The invention of the transistor in the late 1940s at Bell Telephone Laboratories marked a profound turning point in the history of electronics, initiating the shift from bulky and inefficient vacuum tubes to smaller, more reliable, and less power-hungry semiconductor devices. The 1950 publication detailing the initial discovery and characterization of the transistor effect, authored by John Bardeen, Brattain, and implicitly William Shockley, though he is not explicitly listed as a co-author on the original demonstration device publication, stands as a foundational document in the field. This essay provides a critical evaluation of the scientific claims presented within this landmark work, examining the experimental evidence, theoretical framework, and the subsequent reception of the presented findings. The evaluation will proceed through a section-by-section analysis, scrutinizing the argumentation and assessing the overall impact of this seminal contribution. Section 1: Introduction to the experimental setup and the initial observations. The initial sections of the 1950 Bardeen and Brattain publication meticulously describe the experimental apparatus employed to observe the transistor effect. These sections outline the construction of a point-contact transistor, utilizing a germanium crystal as the semiconducting material. A crucial claim presented is the observation of current amplification, achieved by injecting current into one point contact and observing a corresponding increase in current in a second, closely spaced point contact. The authors detail the procedures used to ensure good electrical contact between the metal points and the germanium surface, emphasizing the importance of surface treatments and pressure adjustments. A critical evaluation reveals the limitations inherent in this early experimental setup. The point-contact transistor was inherently unstable and exhibited significant variability in performance, largely due to the sensitivity of the device to surface conditions and the precise positioning of the point contacts. Furthermore, the theoretical understanding of the underlying physical mechanisms was incomplete at this stage, leading to some ambiguity in the interpretation of the experimental results. The authors acknowledge the complexities associated with surface states and their influence on the observed electrical characteristics, but their proposed explanations lack the sophistication of later surface physics theories. The reliance on empirical observations, while crucial for the initial discovery, also limited the ability to predict device behavior and optimize performance. Section 2: Characterization of current amplification and transconductance. A significant portion of the 1905 paper is dedicated to characterizing the current amplification properties of the point-contact transistor. The authors present measurements of current gain, defined as the ratio of the change in output current to the change in input current. They also introduce the concept of transconductance, which quantifies the change in output current for a given change in input voltage. These parameters were essential for evaluating the performance characteristics of the device and comparing it to existing vacuum tube amplifiers. A detailed analysis of the presented data reveals several noteworthy observations. The measured current gains were typically modest, often less than unity, indicating that the device did not provide substantial amplification in all cases. The transconductance values, while demonstrating the potential for signal amplification, were also subject to significant variations depending on the specific device configuration and operating conditions. The authors attribute these variations to the complex interplay between surface states, contact resistance, and the injection efficiency of the point contacts. The paper notes that high reverse voltages could damage the device. This indicates there was significant room for improvement and stability. Examination of the methodologies reveals that the measurement techniques employed were relatively unsophisticated by modern standards. The authors relied on analog meters and manual data recording, which introduced limitations in accuracy and precision. Furthermore, the absence of detailed error analysis makes it challenging to assess the reliability of the presented results. Despite these limitations, the characterization of current, amplification and transconductance provided crucial insights into the fundamental operating principles of the transistor. Section 3, Investigation of Frequency Response and Power Amplification. The 1950 publication also explores the frequency response and power amplification capabilities of the point-contact transistor. The authors present experimental data on the frequency dependence of current, gain and transconductance, demonstrating that the device could operate at frequencies significantly higher than those achievable with conventional vacuum tubes of comparable size. This was a critical advantage, paving the way for the development of high-speed electronic circuits. A crucial claim is the demonstration of power amplification, achieved by using the transistor to drive a load resistor and deliver a larger output power than the input power. The authors quantify the power gain and discuss the factors limiting the maximum achievable output power. A critical evaluation of this section reveals several important considerations. The frequency response of the point-contact transistor was limited by the transit time of carriers across the active region, as well as by parasitic capacitances and inductances associated with the device structure. The authors acknowledge these limitations and discuss potential strategies for improving the high-frequency performance, such as reducing the spacing between the point contacts and optimizing the device geometry. The demonstration of power amplification, while significant, was also subject to limitations. The available output power was relatively low, and the device exhibited significant distortion at high power levels. These limitations were primarily due to the nonlinear characteristics of the point contacts and the limited heat dissipation capability of the germanium crystal. The study also acknowledges several competing explanations for the observed effect. Section 4, Theoretical Interpretation based on surface phenomena. The 1905 Bardeen and Brattain paper offers a tentative theoretical interpretation of the transistor effect, based on the concept of surface states under germanium crystal. The authors propose that these surface states act as traps for electrons and holes, creating a space charge region near the surface. They argue that the injection of current into one point contact modulates the charge distribution in this space charge region, which in turn affects the current flow between the second point contact. A central claim is that the surface states play a crucial role in determining the electrical characteristics of the transistor. A critical analysis reveals the strengths and weaknesses of this theoretical interpretation. The concept of surface states was relatively new at the time, and the authors' understanding of their properties was limited. Their proposed model, while providing a plausible explanation for the observed phenomena, lacked the rigor and predictive power of later semiconductor physics theories. The authors acknowledge the complexities associated with the surface states and emphasize the need for further research to fully elucidate their role in the transistor effect. The theoretical framework presented in the paper was largely qualitative, lacking detailed mathematical models to quantitatively predict device behavior. This limited the ability to design and optimize transistors for specific applications. The paper does, however, represent a first step into new theoretical territory. Section 5. Comparison with existing vacuum tube technology. A significant aspect of the 1950 publication is the comparison of the transistor with existing vacuum tube technology. The authors highlight the advantages of the transistor in terms of size, weight, power consumption, and operating voltage. They also discuss the potential applications of the transistor in various electronic circuits, such as amplifiers, oscillators, and switches. A key claim is that the transistor offers significant improvements over vacuum tubes in terms of efficiency and reliability. A critical evaluation of this comparison reveals several important points. The transistor was indeed significantly smaller and more energy efficient than vacuum tubes, making it ideally suited for portable electronic devices. The lower operating voltage also simplified circuit design and reduced the risk of electrical shock. The authors accurately predicted the potential applications of the transistor in various electronic circuits, but they underestimated the time and effort required to develop practical transistor-based systems. The early point-contact transistors were inherently unreliable and difficult to manufacture, which hindered their widespread adoption in the immediate aftermath of their invention. The comparison to vacuum tubes also downplays some of the limitations of the early transistors, such as their lower power output and higher noise levels. Despite these limitations, the comparison effectively highlighted the transformative potential of the transistor and its ability to revolutionize the field of electronics. Section 6 Impact on Subsequent Research and Development. The 1950 Bardeen and Brattain publication had a profound impact on subsequent research and development in the field of semiconductor electronics. The paper stimulated intense interest in the transistor effect and spurred numerous research groups to investigate the properties of semiconductors and explore new transistor designs. A crucial claim is that the publication served as a catalyst for the rapid advancement of semiconductor technology. An evaluation of this impact reveals several key developments. The publication led to a deeper understanding of the physics of semiconductors, including the role of impurities, crystal defects, and surface states. It also inspired the development of new transistor fabrication techniques, such as Zuckerine junction and alloy junction methods, which yielded more reliable and reproducible devices. The publication also played a crucial role in the development of integrated circuits, which combined multiple transistors and other electronic components on a single semiconductor chip. This innovation revolutionized the field of electronics and paved the way for the development of modern computers, smartphones, and other advanced electronic devices. While the paper was a foundational document, it is important to acknowledge that the initial point-contact transistor was quickly superseded by the junction transistor developed by Shockley, which offered superior performance and stability. However, the initial publication provided the crucial spark that ignited the semiconductor revolution. Section 7 Contemporary Reception and Critiques. The 1950 publication received significant attention within the scientific community, but it also faced skepticism and scrutiny. Some researchers questioned the validity of the experimental results, while others challenged the theoretical interpretation. A central claim is that the publication sparked considerable debate and controversy among scientists. A critical examination of the contemporary reception reveals several interesting perspectives. Some researchers initially struggled to reproduce the results of the Bardeen and Brattain experiments, due to the sensitivity of the point-contact transistor to surface conditions and the precise positioning of the point contacts. This led to doubts about the reliability of the device and the accuracy of the presented data. The theoretical interpretation based on surface states also faced criticism, as the understanding of surface physics was still in its early stages. Some researchers proposed alternative models to explain the transistor effect, based on different physical mechanisms. Despite the skepticism and critiques, the publication ultimately stood the test of time, as subsequent research confirmed the validity of the experimental results and refined the theoretical understanding of the transistor effect. The development of the junction transistor by Shockley and the subsequent work on integrated circuits solidified the importance of the transistor and its transformative impact on the field of electronics. Section 8 Shockley's contributions and the development of the PN junction transistor. While Bardeen and Brattain are credited with the first experimental demonstration of the transistor effect, William Shockley played a crucial role in developing the theoretical framework and the subsequent invention of the PN junction transistor. His work, published in the late 1940s and early 1950s, provided a more rigorous and comprehensive understanding of semiconductor physics and device operation. A key claim is that Shockley's contributions were essential for the development of practical and reliable transistors. A critical assessment of Shockley's work reveals several significant contributions. He developed the theory of PN junctions, which described the behavior of charge carriers at the interface between type and N-type semiconductors. This theory provided a foundation for understanding the operation of junction diodes and transistors. He also invented the junction transistor, which utilized p-n junctions to control the flow of current between the emitter, base, and collector terminals. The junction transistor offered significant advantages over the point contact transistor, including higher gain, lower noise, and greater stability, while Shockley's omission as a co-author on the initial experimental paper has been a point of contention. His theoretical contributions and the invention of the junction transistor were undeniably crucial for the widespread adoption of transistor technology. He correctly posited the importance of bulk properties as opposed to surface states. Section 9 later revisions and refinements of the theory. The initial theoretical interpretations of the transistor effect, presented in the 1950s, underwent significant revisions and refinements in subsequent years. As the understanding of semiconductor physics deepened, researchers developed more sophisticated models to explain the behavior of transistors and other semiconductor devices. A key claim is that the theoretical framework for understanding the transistor effect evolved significantly over time. A critical analysis of these later revisions reveals several important developments. The development of band theory provided a more detailed understanding of the electronic structure of semiconductors and the behavior of charge carriers. The introduction of the concept of energy bands allowed for a more accurate description of the energy levels of electrons in a solid, and the movement of electrons through the crystal lattice. The development of the drift diffusion equation provided a mathematical framework for describing the transport of charge carriers in semiconductors, taking into account the effects of electric fields and concentration gradients. This equation became a fundamental tool for analyzing and simulating the behavior of semiconductor devices. The development of surface physics led to a better understanding of the properties of surface states and their influence on the electrical characteristics of transistors. Researchers developed techniques to control the density and energy distribution of surface states, which improved the performance and reliability of transistors. Section 10 Long-term impact on digital computing and beyond. The invention of the transistor and the subsequent development of integrated circuits had a transformative impact on digital computing and numerous other fields. The miniaturization, increased speed, and reduced power consumption of transistors enabled the development of smaller, faster, and more energy-efficient computers, paving the way for the digital revolution. A central claim is that the transistor revolutionized digital computing and enabled the creation of modern electronic devices. A critical assessment of this long-term impact reveals several key aspects. The transistor enabled the development of microprocessors, which are the central processing units of modern computers. Microprocessors consist of millions or even billions of transistors integrated on a single semiconductor chip, allowing for complex calculations and data processing at incredibly high speeds. The transistor also enabled the development of memory chips, which store data in the form of electrical charges. Memory chips are essential for storing the operating system, application programs, and user data in computers, smartphones, and other electronic devices. The transistor also revolutionized telecommunications, enabling the development of mobile phones, wireless networks, and other communication technologies. The transistor is an integral part of nearly all modern technology. Section 11 Enduring legacy and continued relevance. Despite the advancements in semiconductor technology over the past several decades, the 1950 Bardeen and Brattain publication continues to hold significant historical and scientific relevance. The paper represents a pivotal moment in the history of electronics, marking the transition from vacuum tubes to semiconductors and laying the foundation for the digital age. A key claim is that the publication remains a testament to the ingenuity and perseverance of the scientists who invented the transistor. A critical reflection on the enduring legacy of the publication reveals several important considerations. The paper serves as a reminder of the importance of fundamental research in driving technological innovation. The discovery of the transistor effect was the result of curiosity-driven research aimed at understanding the properties of semiconductors. This discovery had profound implications for society leading to the development of countless new technologies and transforming the way we live and work. The paper also highlights the collaborative nature of scientific discovery. The invention of the transistor was the result of the combined efforts of Bardeen, Brattain, and Shockley, each of whom brought unique skills and perspectives to the project. The story of the transistor underscores the importance of teamwork and interdisciplinary collaboration in addressing complex scientific challenges. It is the progenitor of nearly every modern electronic device. In conclusion, the 1950 publication by Bardeen and Brattain detailing their initial observations of the transistor effect stands as a monumental achievement in the history of science and technology. While the initial point-contact transistor was quickly superseded by junction transistors, the publication provided the crucial spark that ignited the semiconductor revolution. The experimental evidence presented, the theoretical interpretation offered, and the subsequent impact on research and development all contribute to the enduring significance of this seminal work. The essay's section-by-section analysis has revealed both the strengths and limitations of the claims made within the paper, highlighting the complex interplay between experimental observations, theoretical understanding, and technological innovation. The publication serves as a powerful reminder of the transformative potential of scientific discovery and the importance of continued investment in fundamental research. The transistor represents a paradigm shift, the echoes of which continue to resonate throughout the modern technological landscape.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.